Welcome to part 2 of the Glacier Mass Balance lectures. My name is Andrew Mercer and I will be giving a brief introduction to the basic processes of glacier mass balance. In the previous lecture, we looked at the balance between accumulation and ablation, in both space and time. We noted that both processes occur in both zones and in both periods. This map shows the winter mass balance, or surface accumulation, for Stockholm in 2011. Note the distribution of mass over the glacier. High accumulation in the upper reaches of the glacier and low accumulation lower down. We will return to this map shortly for further discussion. Here we see the summer mass balance, or surface ablation, for Stockholm in 2011, and the sum of these then is the net surface mass balance. All of these have been shown with meters of water equivalent. Returning to the accumulation map, we can see clear differences in the distribution of mass on the glacier surface, and whilst we can see a generally decreasing trend with elevation, there are also other patterns that invite discussion. Looking at a profile along the glacier for the 2011 winter, from the northern niche, where most accumulation occurs on Stockholm, through to the centre line down to the front, we can clearly see that accumulation increases in the lee produced by peaks and brows. This effect can be seen near the front, though in 2011 the relative increase was not great. We also see a suggestion of reduced accumulation upwind of this brow due to an increased wind speed at this point. This effect can be seen on the map in at least two locations, which I leave to you to identify. Also on the map, we can see the lee effect out from the centre line of the glacier with increased accumulation along the lateral edges. There are other more curious features on this map. The conic forms of the accumulation pattern in these locations is due to the interpolation of data between measured values. At these locations, the values diverge considerably from the local mean, due either to strong localized effects, errors in the survey, or both. The conic pattern may be considered an artifact, though the readings at specific points may be correct. Averaged over many years, the pattern of snow depth distribution looks like this, with blue indicating greater snow depth and red lesser snow depth. The snow depth distribution is very similar to the accumulation distribution, for obvious reasons. This map shows average snow depth at discrete points, with no interpolation, and so the conical forms cannot be seen, but still some steep gradients can be discerned. Here, for example. Higher up on the glacier we see there are missing values. These areas of the glacier are steep and crevassed. They are considered too dangerous to survey, but as can be seen here, they have varied snow cover and topography. This introduces a not inconsiderable uncertainty into the surface mass balance calculation, but is unavoidable. We have focused so far on snow depth, which is perhaps the first and most obvious variable in surface accumulation, but snow density is equally important. On Stockholm, 6 density pits are dug, 5 along the centre line and 1 in the northern niche accumulation area. The 6 density profiles show variation in the density of snow with depth, and it is quite clear that the snowpack at lower elevations is more homogeneous than at higher elevations. The snow has been more greatly influenced by secondary processes. It has been compacted by wind and experienced more and greater melt events than the higher elevation snowpack. Looking more generally at the transformation and densification of the snowpack, we start by looking at new snow. New snowfall can have a density of between 20 and 120 grams per cubic centimetre, though 60 grams per cubic centimetre is more typical as a lower boundary. The upper boundary depends on the temperature of the snowfall. Rain-mixed snow and sleet will have a higher density than dry snow, and high wind speeds increase the wind packing of the new snow. High winds break the snowflakes into smaller, rounder crystals, allowing more dense packing, as well as the mechanical forcing of the snowpack by the wind. Once snow has formed a snowpack, it then begins the transformation to firn and then ice. By definition, Firn is any snow that has survived from one accumulation season to the next. In high Arctic glaciers and ice sheets, this definition may be at odds with typical density figures given for firn, due to the dry, low precipitation conditions prevailing there. On mid-latitude glaciers, however, firn density may be reached even before the end of the accumulation season. Throughout the snowpack of a typical mid-latitude glacier, ice lenses may be found. These occur where water, either from rain or melt loss, loses enough energy to refreeze into the snowpack. At the base of the snowpack, above the firn layer, that is last year's summer surface, a layer of depth hoar will usually be found. The density of this is somewhat lower than the layers above, with large ice grains giving large pore spaces. Depth hoar is created when the temperature gradient in the snowpack causes a strong vapor pressure gradient, which then causes the sublimation of snow crystals and the subsequent redeposition around other crystals. This effect is usually strongest over ice, which is reflected in the profiles of the density pits. Those in the accumulation area show a less distinct depth hoar formation. In summary, accumulation is the snow depth multiplied by the snow density. Simple enough, but this simple sum can be interpreted and performed in many ways before a glacier-wide accumulation is calculated. In part 3, we will look at ablation.